All right, hello everyone. My name is Natalie Bombardieri, and I'm a recent graduate from the University of Alberta. Today, I'll be talking about my work improving deep localized level analysis, how game logs can help. So, the field that we're concerning ourselves with is player modeling, which is the process of studying players in order to learn more about them. Low-level game information, such as records of what happened in a game during a play session, also known as game event logs, are often crucial to this application. There's a couple problems in this field which we try to address with this work. The first problem is a lack of transferability. So if you make yourself a log for a game like Minecraft, it might take a whole lot of work in order to make it work with Mario Bros, even if it's transferable at all. Another problem in the field is the lack of available game event logs. So oftentimes these are safely guarded by whoever made the game, or they're just not available at all, period, which makes it really hard to do player modeling without them. So what did we do? Our proposed solution is to train a deep neural network on a game where we have both level information and log information, and then take away the log information and use a game that only has level information in order to test our model. So, taking that away, let's look at some past work. Past work by Lau, Gusdile, and Riddell uses this approach, similar approach to ours rather, and we use it as a benchmark for our performance. They use convolutional neural nets in order to predict player affect, predicting player ratings of Mario levels based on gameplay logs and level inputs. Our work differs by focusing on small moments of gameplay rather than entire summary play sessions that are fed in. Another approach to creating player modeling systems that transfer between games is a recent work by David Malhart, which neural nets are trained on one game and then used to predict player affect on other games. The drawback to this approach is that it does still rely on having logs for both games. So what did we do? Well, first, we improved deep level and log analysis over the state of the art. We outputted what our model thinks is interesting or fun and showcase that. And lastly, we test our model's capability to learn patterns between games that we haven't trained it on. So first, I'll look at the data set. We're using a data set that was conducted on the Infinite Mario Bros. Game, which was produced by Gusdile and Riddell, game level generation paper. Sorry. The dataset was collected from a human subject study where players played 3 Mario levels each from a set of 15 levels, and then were asked to rank each of the levels in order from most to least on metrics of fun, challenge, and frustration. The dataset looks a little bit like this. There's a little screenshot of what it sort of looks like. We have gameplay logs up in the top and level information down there. And we actually have complete information of what the players did and the maps that we have players playing. So, looking first at the logs, this is represented in a multi-hot array where everything that happens in-game is recorded by these arrays of ones and zeros and some other values as well. In this picture, we see Mario jumping, as shown by the jumping column where there's a bunch of ones and then landing right at the end of the zero. And during this entire time, Mario is in the little state. That's shown over in the far right. We also include information such as the level being played, Mario's exposition, the familiarity of the player with Mario games, and what was the final one? No, that's it. Lastly, the Mario exposition wasn't actually included in the dataset, so instead we calculate that using Mario's movement speed and the amount that Mario's moved in the current play session. Next up is the level chunk information. So we're using localized level information, which means we only use a small portion of the level around Mario's position at each given time, rather than using an entire level as input. So that's going to make it look a little bit more like this white square is what our model is going to see, rather than a whole level all at once. We provide our model with a 10 by 10 chunk of the level information, and we calculated Mario's position that we used to get that level chunk in the previous slide. This data is kept in the form of one hot array, in each XY position having one tile flag active. Each data point contains 3 level chunks from the middle, beginning, and final time steps of the time span of the given data point that we're looking at. In our work, that would mean, since we're using 10 frames, we have the level chunk from the first, middle, and last frame. So going forward, our model's goal, as a reminder, is to take in level information and log information and combine these into the ranking system that was provided in the data set. So this is going to be ranking if a level was rated most, mid, or least, frustrating, challenging, or fun, based on the metric that we're trying to measure. All right, so let's take a look at the model. We're taking in each data point as a 5,470 by 1 array. Then we're splitting out the first 370 values of that array, and that represents the logs for those 10 frames, as well as 3 level chunks, which are 1,700 values in size. Looking first at the logs head of our model, we take our logs, feed them through a convolution layer, then through a max pooling layer, and finally through another convolution layer. Next up, looking at the level chunk parser, we feed it again through a convolution layer, then a max pooling layer, and finally through another convolution layer. Once we've done that, we feed them back together, have a dropout layer where we keep 98% of data points, and finally feed into a fully connected layer, which then feeds into our output layer. Once again, since we have 3 values in the output layer, that's representing predictions of most, mid, and least for each of the metrics that we're measuring. Moving forward, we're going to look at the evaluation of our model. So as I mentioned earlier, we're using the Infinite Mario Bros dataset from Gwario and Riddell to train our model, as well as test its initial accuracy. Then we are using the Gwario dataset, which was provided by Kristen Sue, Matthew Gwario, and Riddell. And lastly, we are using, Lastly, we're using the VGLC, which contains original Mario levels, which is provided by Adam Somerville et al. So with a quick look, let's check out our first experiment. This is the Infinite Mario Bros experiment. And as I outlined before, we're using the data set that has player rankings of fun, frustration, and challenge rather. And we're trying to predict those rankings. So we're using this data set to train our model, and we use an 80-10-10 train, test, validate split. And we're measuring the accuracy of our model on the test set. The model is given a data point and predicts the rating assigned to the level by that player. Our results here, not coming up. Our results here are shown in the top row of that column, or of that table, where we're achieving about 92% accuracy or 90% accuracy across the board, compared to the past state of the art, which is achieving around 82% accuracy. It looks like we're onto something by looking at localized log and level of information. So now let's take a look at what our model thinks is fun. So here are some screenshots of 5x5 level sections that maximally activated our model's fun filter. And this is a reminder that we do not actually tell it anything about the game or what is fun. This is what the model has decided is interesting or fun. And looking at it, you can see some challenging or interesting sections of gameplay. Here you might have 2 enemies, or over there in that third picture, you'll have yourself jumping up and then having to duck under a bullet bill, which are all interesting in their own right. This is, once again, an avenue for future work where we have our model being able to give game designers interesting information about what is fun in the games that they're making and how to create more interesting level design patterns. Next, we're going to test our model without logs. So as a reminder, this is originally what our model is doing and how we're training it. And then we're going to take away those logs and only train it using level information. I'm going to take a little sip. All right. The next data set we're using is from Gwario, which is a clone of Super Mario Bros. The Lost Level, and it was used to collect gameplay data and level ratings. We adapt their data set for our work. In Gwario, the experiment uses a 1 to 5 Likert scale rating, whereas we use most, mid, and least rankings for our system. So we have to convert these into our most, mid, and least ranking systems to adapt them for our data set. And we do this by calculating the mean ratings for each level, putting them together, and then ordering the highest rated levels as the most, the 2 middle ranking levels as the mid, and the lowest ranking for each metric as the least. This data set also lacked log files, so instead we create empty log files with all zeros as the data and advancing Mario's exposition by 1 in each frame. Oh, sorry, here's an example of just the empty logs that we had. So the evaluation. If we're looking in the top row, we have our model trained originally on the logs and level. And this is achieving a 38.7% accuracy, 41.2% accuracy, and 37.5% accuracy, compared to a level-only analyzer, which is getting 47% accuracy, 27.9% accuracy, and 29.4% accuracy. This is meaning our approach is more consistent, as the model that was trained only on visual level information rather than log information was generally just picking one rating and then only outputting that. We're also getting a little bit lower accuracy than before because the labeling distances seem to be causing a bit of a problem, which is actually a bit of an inspiration for our next experiment. With the final experiment of our work, we test our model's ability to learn meaningful information. So we conducted an experiment on 16 levels from the original Mario Bros. Game. Rather than assigning ratings to the levels, we instead measure the mean challenge prediction for each level to see if the level number and accuracy are increasing, or rather the level number and difficulty are correlating. We expect that the levels would increase in challenge throughout the game, and if our model's predictions show a positive correlation between level number and challenge, that would signify that our model is able to meaningfully learn level features across games without the need for log files. We use a Spearman's row correlation test to verify if challenge and level number are correlated. As a reminder, our subscript S on the next slide is going to denote if a prediction is increasing in frequency or decreasing in frequency. So how does it look? Here's the table of output for level number and the different challenge ratings, with most on the left, mid in the middle, and least on the right. As we can see, as the level is progressing, we're getting higher amounts of most challenging and fewer amounts of least challenging. And then if we actually look at the numbers, we have ourselves in this table positive numbers for the R score of most and mid, and a negative score for the least, which means, in fact, our assumption is correct, that challenge is increasing as the game is progressing. All of these values are statistically significant, and the ranges for a confidence interval of 95% keep them still in the positive or negative range. So that's great. Our model is learning something useful. Some future work that we would like to highlight is possibly creating levels using top scoring fun level chunks and testing those to see if they're any fun, as well as adapting the model for use with different games with less in common with Mario games. In conclusion, our contributions include improving deep neural network affect prediction using localized level logs, localized level information and log information, as well as presenting a new method of training level analyzers using supplementary data that is not available at test time. I thank you all for your time, and I'll open the floor for questions now.